Hey guys, this is Wes. This is the second video in a series about the external bus interface on the XMEGA 128A1U microcontroller, which for the rest of the video I will be referring to as just the XMEGA. In the previous video, you were shown a couple of different ways to connect switches to the I/O ports on the XMEGA. While the last method was much better than the first method in terms of the amount of hardware required, it still requires us to manually configure the output enables for these tri-state buffers before we can actually load the correct data into the XMEGA. So the solution that we're going to employ in this video takes advantage of a native mechanism to the microcontroller that will create a more fluid and dynamic solution than the methods from the first video. This solution is ultimately based on a technique known as memory mapping, in which different peripherals such as memories, LCDs, I/O registers, external devices, etc. are accessible via unique addresses or ranges of addresses. So to contrast this from the previous example, when memory mapping is used, we can access addresses that have been assigned to communicate with external devices such as switches, instead of having to manually enable them like we were doing in the previous video. So to be able to fully understand our new solution, we should first take a step back to evaluate how memory mapping is used within the XMEGA. One example of this that you've already indirectly dealt with is the set of all internal system registers within the XMEGA. This collection of registers is referred to as I/O memory within Atmel's documentation and is mapped to addresses 0 through FFF. This is just a small region within the entire data memory map of the XMEGA. A critical component we must understand is that to access any of these internal system registers, such as CPU ramp Z, port AN, or TCC0 control A, a very specific address must be either read from or written to. In the context of CPU ramp Z, for example, this specific address is hex 3B. The specific address for port AN is hex 608, so on and so forth for all of the internal system registers. The addresses that correspond to each of these registers can be found within the manuals as well as the include file that's provided. Now, in an attempt to relate this to the previous example, anytime we wanted to read the data value corresponding to any of these DIP switches, we would have to eventually read the port A in register, which would ultimately require us to perform a load instruction from the address 608. This may seem relatively straightforward to understand at a higher level, but for us to come up with a better solution, we must first know exactly what's going on at a more fundamental level. So in the context of this example, we should ask ourselves, how exactly does this memory mapping work, and what allows port A in to be accessible via this single address hex 608. Let's consider, for example, the configuration of an internal register such as port A in within the XMEGA. Port A in this diagram corresponds to the 8 physical pins on the XMEGA that collectively represent port A. There's a lot of miscellaneous hardware between the physical pins on the microcontroller and the port A in register. All you need to know is that this hardware can be configured in many different ways, and it just ensures that only logical zeros or ones end up in the port A in register, depending on the voltage value present on the physical pins. For this example, when a load instruction takes place, the data from the port A in register needs to be present on the data bus so that it can be loaded into a general purpose register such as R16, R17, etc. To accomplish this, there is a tri-state buffer between the output of the port A in register and the data bus. For the same reason, there was one between the DIP switches and port A from the previous example. Because port A is memory mapped, it needs to only be accessible from address hex 608. Another constraint is that it is a read-only register. In other words, software should not be able to store any data within it. This means that this tri-state buffer should only be enabled when address 608 is being read, and only when it's being read, not if it gets written to. The act of only enabling a device when a specific combination of address bits is true is referred to as address decoding. So here I have a timing diagram, and this approximates what's going on within the XMEGA when a load from the port A in register, which corresponds to this address, is executed. So the last piece to the puzzle in this diagram is the output enable signal, which we have left as a question mark in this diagram. So as I mentioned previously, the output enable signal must only be true for this unique address, and only when the read enable signal is true. For example, if write enable was true, or if this were any other address, the output enable signal should be false. One more thing to mention here is that the output enable signal in this case is active high, because as seen in this previous diagram, it's indicated here as active high. So back to the timing diagram, I'm going to go ahead and draw what we know the output enable should look like at this point in time. So when the read enable signal is true and the unique address that corresponds to port A in is true, I want the output enable signal to be true, which would be high. So I'll draw that. And at all other times, i.e. when the address is anything besides 608, or when read enable is false, I want to have output enable be low or false, so that the tri-state is not enabled. Now we're going to take a look at the Boolean equation we would need to actually generate this signal. Then we'll determine how it could be implemented in hardware to ultimately connect to the output enable of the tri-state buffer. So the output enable signal will be denoted as a function of the address bits, which is here, and the read enable signal, which also needs to be true to enable the tri-state buffer. So to go about finding the combination of address bits that needs to be true, we base that off of the address. So it may help you to write the address in a binary representation first, and then go from there. So this will be A0 all the way up through A11. So something that's very important to note is that the address bus is 24 bits wide. So because this should be the only combination of address bits, so from A23 all the way down to A12 being 0, and A11 through A0 having this combination, that's the only case where this signal should be true. Okay, so now we just need to start generating this equation where any bit that should be 0 will be knotted, and any bit that is a 1 will not be knotted. So I'm going to abbreviate the upper bits just to save time, like this, and then proceed with the lower 12 bits. So A11 will be knotted, A10 and A9 will not be knotted, A8 all the way down through A4 will be knotted, A3, and then A2 down through A0 will be knotted. So when this unique combination of address bits is true, we want output enable to be true. The last thing remaining is the read enable signal. So because we only want to be able to enable this tri-state buffer when read enable is true, we have to include it in our equation for the output enable. Now that we have a Boolean equation for the output enable signal, we can start to take a look at how we could potentially implement this in hardware. So I'm going to go ahead and copy this over to the block diagram that we had earlier for port A in, and I'm going to paste it so that I can use it as a reference for when we're designing this hardware. So the most obvious way, or first thing that would come to mind to implement this equation to hardware, would be to use AND gates, since everything is just ANDed together in one long sequence. So to quickly demonstrate this, I'm going to use an imaginary 25 input AND gate. And for the sake of time, I'm not going to fill in every single signal similar to the way I did here by abbreviation. So for any signal that is knotted in this Boolean equation, I'm going to make it an active low input to the AND gate. So A23 through A11 are going to be active low inputs. A10 and A9 are going to be active high inputs, so on and so forth for the rest of the address lines. And then we can't forget the read enable signal, which on the XMEGA is an active low signal. So I will designate it as such and make sure that I have a bubble denoting it's an active low input. So that should be all the 25 inputs we need to generate the output enable signal, which I will call output enable, which is going to be an active high signal. So now we can replace this question mark with output enable high, and we have now ensured that port A in will only be connected to the data bus when this specific combination of addresses, or hex 608, is being loaded by the processor. So now that we understand more about how memory mapping can be implemented with address decoding, let's go take a look at our original problem again of interfacing with external devices such as switches in our case. As mentioned previously, it would be nice if we could automatically interface with separate external entities by memory mapping them, as opposed to the process we used in this example of manually configuring each control signal before we accessed the external devices. Thankfully, the XMEGA has its external bus interface, or EBI, that allows us to do this while abstracting away most of the complex address decoding that's required. So to introduce the EBI of the XMEGA, I'm going to point out a few key features from the manual, and this is the Doc 8331 manual if you're following along. So the EBI is used to connect external peripherals and memory for access through the data memory space, which, as you know, is much less tedious than manually configuring control signals yourself, as we proposed in our original solution. So a couple more key things I wanted to point out specifically from the manual is that it advertises EBI as exactly what we want it to be. We want to be able to access external devices via memory access instructions, as opposed to manually configuring control signals every time we want to interface with a device. So this will allow us to interface with several different types of components. For example, SRAM, LCD displays, ROM, I/O ports, keypads, etc. Here we have the entire memory map available to the XMEGA. We have I/O memory, which we've previously discussed. We have EEPROM, as well as internal SRAM, which is commonly referred to as data memory, as well as a very large region that's dedicated to interfacing with external peripherals. So when you begin designing your system, you have a blank canvas to work with, which is the address range of hex 4000 all the way to the end of the memory map, which is when all 24 bits of the address would be set. So the difficult part of EBI to understand for a lot of students is the idea that we are simultaneously enabling and accessing external devices using load and store instructions instead of manually selecting external devices via software-controlled signals, similar to the way we did it in the previous solution. This may be hard to grasp at first, but remember it's the reason EBI is so useful. When configuring EBI, before deciding where in memory you're going to map your peripherals, you must decide which EBI mode suits your application. In this class, we will always use an SRAM configuration for the external bus interface. This configuration gives us physical access to the address bus, the data bus, as well as all of the control signals necessary for most typical applications that are specific to the MicroPad 2.0 kit. When using the SRAM configuration, there are 4 different arrangements we can choose from in which we can access all of these interface signals. The different arrangements allow us to customize the way we set up the hardware such that it suits our specific application. Due to the way the MicroPad 2.0 kit is connected, we usually use the arrangement in which address bytes 0 and 1 are time multiplexed on the same bus. This means that we will not have physical access to address bits 20 through 23, but only up to 19. It's set up this way because for the labs in the course, you would never really need to use all 24 bits of the address bus externally. In this context, time multiplexing is just a fancy way of saying that 2 address bytes are present on the same bus at 2 different points in time. This allows the EBI to function using up less pins on the microcontroller overall. The only way this can work is if we use a latch component externally, depicted here, to save the second address byte since it's only present on the bus for a very short period of time. Here we have the same diagram that we've been looking at, as well as a timing diagram that depicts a full EBI read cycle. The purpose of the ALE1 signal is to enable the address latch. And the purpose of the address latch in this arrangement is to make sure the second address byte is always present and available for connection. It is necessary for all of the used address bits to be available at the same time when interfacing with certain components, one example being memory. Before the data gets loaded into the CPU, the second address byte must be latched so that it's available over here on the output. When the ALE1 signal goes high, the second address byte is fed through the latch, and when ALE1 goes low, the address byte is retained. Now when the actual load happens, both the first and the second address bytes are present in hardware at the same time. Afterwards, the first address byte will be asserted onto the bus, and the second address byte will be present in hardware on the output of the latch. At this point in time, whatever data is on the data bus is then loaded into the CPU. Note that even though this setup is coined an SRAM configuration, it can still be used for a wide range of devices that have similar interfaces such as I/O ports, LCDs, etc. The main difference when used with other devices is that the address lines may not always be connected to the external entities, such as with I/O ports. Some devices are very simple and just need an enable signal and the data bus. Although this arrangement is the one we will actively be using in the course, you are also responsible for understanding the other arrangements available for the purposes of the exams. You should understand the difference between all of these arrangements as well as when they should be used or not used. The main similarity between these 2 arrangements is that they give you access to all 24 bits of the address, which could be crucial in some applications that use up the majority of the memory map. After you decide which configuration and arrangement you're going to use, you need to decide where you're going to place your device within the memory map. This involves configuring what are known as the EBI chip selects. The XMEGA has 4 chip selects that control which memory mapped external hardware is accessed when a given memory address is asserted on the external bus interface. In other words, when a load or store instruction within a specified address range is executed, the chip select that is associated with the address range is automatically asserted. The beauty of this is that the XMEGA will internally handle the majority of the decoding logic that is required to make this happen. This means that as the programmer and designer of the system, I can specify an address range for a device or set of devices, and the microcontroller will ensure that I don't have to implement much of my own external logic. There are two main things that must be determined about each chip select. The first thing is the size of the chip select. The second thing is called the base address of the chip select. The base address is just the first address in the range of addresses that is to be associated with each chip select. So the first thing that should be determined is the size. This is often determined by the type of device that is being added. There's a discrete set of possible configurable address sizes between 256 bytes and 16 megabytes. The second thing to determine is the base address. Before you can configure the base address, there are some limitations and guidelines that you must follow. The first limitation is that the base address must be on at least a 4K boundary, where a boundary is defined as an address where a specific amount of the least significant bits are 0. Take 4K for example. This is equal to 2 to the 2 times 2 to the 10, which is equal to 2 to the 12. This would correspond to the lower 12 bits of the base address being 0 to be considered on a 4K boundary. The second limitation of the base address is that it must be on a boundary that is equal to or greater than the size of the desired address range. For example, if I wanted to add an 8K device to the memory map, I would need to ensure that its base address is on at least an 8K boundary. For example, it could not be on a 4K boundary. An important thing to note is that any address size less than 4K must still have a base address that's on a 4K boundary. For example, if I wanted to add a device that was only a 1K address size, I could not put it on a 1K boundary. I have to put it on at least a 4K boundary. Now let's go ahead and take a look at how the XMEGA's external bus interface will be physically connected to external hardware. To accomplish this, I'll be showing you the alternate pin functions within the 8385 device-specific datasheet. They're located in section 33.2. This section lists all of the pins on each port, as well as any functions these may serve for all of the different systems within the XMEGA. Ports H, J, and K must be used to connect to the external bus interface when using SRAM ALE1 mode like we are, as we discussed previously. Port H contains write enable, read enable, ALE1, and all 4 chip selects. It's important to note here that the activation level of ALE1 is actually active high. The documentation is wrong. Port J gives us access to the data bus, and port K acts as the shared bus in which address bytes 0 and 1 are time multiplexed. To summarize, I will do a simple example of adding an external 32K SRAM to the XMEGA using the external bus interface. Because I'm assuming no other external devices are currently connected, I can assume that I have the entire external memory map available, which would be from hex 4000 all the way to the end of the memory map. As I mentioned earlier, the first thing you should do when configuring a chip select is the size. So in this case, because I'm using a 32K SRAM, it's most intuitive to use a chip select that is also 32K. It is important to note, however, that this may not always be the case. In some instances, we may have constraints that we have to work around, such as a limited address range or a very large device. For example, if I was told I had to make an SRAM start at address 4000, I would have to explore other options, such as using multiple smaller 16K chip selects to enable one device, since a 32K chip select would not be able to be placed at address 4000. There are many other possibilities like this, some of which will be exemplified in the following video. Next is the base address. So, because the chip select is going to be 32K, as I've defined here, the base address, as we've defined earlier, must be on at least a 32K boundary. So some 32K boundaries are 0, 8,000, 10,000, etc. all the way throughout the rest of the memory map. So the way you can figure this out is by doing 32K like we did previously is 2 to the 5 times 2 to the 10, which is 2 to the 15. So for a chip select base address to be on a 32K boundary, the least significant 15 bits must be 0. And if you take the time to look, you'll notice that all three of these satisfy that condition. So because the external memory range within the XMEGA's data memory map begins at address hex 4000, I should not use address 0 because it's not within the range I have available. And I cannot use address 4000 because it's only a 16K boundary. And as we defined earlier, the chip select base address must be at least the size of the chip select, and 16K is less than 32K. This leaves me with 8,000 or any address afterwards in the memory map, as long as it's a 32K boundary. So I will assume that I'm going to put it at 8,000. And if it's going to be size of 32K, I need to add 32K to hex 8000, which is going to be 0xFFF. Now I'm going to go ahead and label this section of the memory map corresponding to the device that I'm going to place here. I'm also going to specify which chip select that I'm going to use so that I can keep track if I have multiple devices that I'm adding. Now let's see all the physical connections that will be required to successfully interface with this SRAM. I'll start by filling out all the necessary signals that we're going to actually need from the microcontroller. So if you recall, port K was the shared or time multiplexed address bus. So I'll label it in a way that lets me know that at any point in time it might have either the 0th or 1st address byte. And then port J was simply the data bus. The read enable and write enable signals are both active low, so I'll label them indicating the activation level. It's always good practice to label the activation level when drawing these schematic diagrams for clarity. ALE1, we're not using ALE2, so I don't need to fill it out. I arbitrarily chose to use CS0, so I'm going to just populate that one. And then in this case, I don't need to worry about any of these, but on exams, you might have to use additional ports for some reason. Next, I'm going to go ahead and complete the address latching circuitry over here. So if you recall from the diagram that we analyzed earlier, the input of the latch is the time multiplexed address bus, which I will abbreviate as AA. And then the ALE1 signal will enable the latch when the high byte of the address is on the address bus. This will save the high byte to the output of the address latch. And then when ALE goes back false, the high byte will be preserved on the output of the latch so that we can use it to connect to other devices such as the SRAM. Now to connect the SRAM, remember it's a 32K SRAM. So for a 32K device, that's 2 to the 5 times 2 to the 10 is 2 to the 15. So that's 15 bits that I'm going to need to use from 15 address bits that I'm going to need to use to interface with the SRAM. So that's going to be A14 to A0, 15-bit bus. And because I now have access to A15 to 8 at all times because it's on the output of the latch, I can now use any combination of the lower 2 bytes of addresses I want. So A14 to A0 is what I'm going to need to successfully interface with the SRAM. The write enable and read enable signals are going to connect directly to their respective signals on the SRAM. The data bus is going to be connected to the SRAM. And the chip select that's going to enable the SRAM is going to be directly related to the chip select that we've defined with the EBI. So now anytime I write to an address in this range, 8000 to FFFF, the chip select will go true, which will enable the SRAM, and then depending on if it's a read or a write from the processor, the respective action will happen. Now that we've learned how to use the external bus interface to communicate with an SRAM, let's try to connect an output port. As always, the first thing you need to consider when configuring a chip select is how many addresses it should be represented by in the memory map. For an SRAM, like in the previous example, it was very natural for us to decide the chip select should have been 32K because the memory was 32K in size. But now, with an output port, how big should the chip select be? An output port doesn't even use any address bits directly because it's just a register, as you can see here. A register is simply a combination of more than one flip-flop in parallel with a shared clock input. In this class, we use 8-bit flip-flop chips as our output ports as opposed to other similar devices such as latches, because flip-flops almost always have shorter setup and hold times, which leads to more precise and timely outputs. This is out of the scope of this course, so I won't go into detail about it here. Just know that we always use a flip-flop chip for our output ports. So now that we know we're using a register, how are we going to connect it, and what's going to be different between it and the SRAM we connected previously? To answer this question, we must first understand the difference between full and partial address decoding. Full address decoding is when all of the address bits that are not connected to the external device are used for address decoding. Full address decoding is when all of the address bits that are not connected to the external device are used for the address decoding. An example of this would be the SRAM we connected in the previous example. We used the lower 15 address lines to connect to the SRAM, and all of the higher address lines were used in decoding of the chip select. Thus, the SRAM was fully address decoded. Partial address decoding is when not all of the address bits are used in the address decoding, and therefore act as don't cares. So with respect to the output port, because none of the address bits are connected directly to it, all 24 of the address bits would have to be used in the decoding logic for it to classify as being fully address decoded. In the chip select control A register in the manual, you can see which address bits are used in decoding the chip select for each address size. Even for the smallest address size of 256 bytes, only address lines 23 through 8 are used to decode the address. This means that address bits 7 through 0 are not being used, and therefore the output port is being partially address decoded if we chose this size, or any other larger size for that matter. So to fully address decode the output port, we would need to externally address decode bits 7 through 0. So now that we know the difference, we will choose to stick with partially address decoding the output port such that we don't have to use as much external logic. With that being said, let's arbitrarily choose a chip select size of 4K for our output port. Since address 4000 is the first address available in the memory map, and it happens to be a 4K boundary, I'll choose that as the base address. So I'll put my output port from hex 4000 through hex 4FFF and label it 4K output. And let's say we want to use chip select 1 this time instead of chip select 0. So now let's connect all of the necessary components like we did with the SRAM. So here we have a basic diagram including the XMEGA and an 8-bit flip-flop device that will serve as our output port. I've already labeled all of the necessary signals to save time. Note that I do not need the ALE1 signal in this example since I'm not using the second address byte, A15 to A8, to connect to any of my external devices. I'll start by connecting the data bus to the flip-flop, and I'll label the output of the flip-flop out 7 to 0. because the output can be connected to anything the designer of the system would like, and a common example being LEDs. Now the last thing we have to do is connect the rising edge triggered clock input to the flip-flop. Unfortunately, this is not going to be as simple as just connecting chip select 1 directly to it. To help us determine what we need to connect to this clock signal, let's analyze an EBI write cycle from the manual. We need to somehow create a signal that generates a rising edge when the data is on the data bus that we want to output to the output port. What combination of these control signals will accomplish this? Let's add a signal to this timing diagram and depict how we would like it to behave. This will allow us to develop some circuitry to generate the proper clock input signal. So I'm going to make a new signal here and call it out control, because it's going to be the control signal to our output port. And remember, I want a rising edge when the data that we want to go to the output port is on the data bus. So that happens to be in this region right here. So if you kind of make an observation, if you see when the right enable signal goes high, that's more or less exactly where we want our output control to also have a rising edge. So I'm going to model my out control signal off of the right enable signal. Now, one thing you may be thinking is, well, why can't we just tie the right enable signal directly to the output port? And while this will work in some cases, this would write to the output port on any write cycle, no matter the address, which would be incorrect. We only want to be able to write to the output port when we write to an address that's within our chip select range. So, if that's the case, since the chip select is what determines whether the correct address has been accessed or not, we can AND the chip select with write enable. And this will give us a basic foundation of where to start generating this circuitry. So if we go ahead and call this Boolean equation, or the output of this Boolean equation, output control, our goal now is to create an AND gate circuit that will generate a low voltage when chip select and write enable are both true. So if we draw an AND gate, chip select and write enable are going to be active low inputs. In this case, we're using chip select 1. So I'm going to have bubbles because they're active low inputs. Because when they're both true or both low, I want to generate a low voltage on out control. So if I want a low voltage when these two ANDed together are true, then I need to have a bubble on the output, meaning that out control will be an active low signal. So now, if I copy this, and I paste it onto the diagram we've made earlier, I now have an output control signal that I can use as the clock input to the flip-flop that will generate a rising edge precisely when we want it to, when the data is on the bus ready to be clocked in to the output port. So that's about it for the second EBI video. We added two external devices to the XMEGA, a 32K SRAM that was fully address decoded, and a partially address decoded output port that was accessible from 4K different addresses. We also learned some critical nuances and limitations when it comes to configuring the chip selects within the external bus interface. So I hope this video helped. There will be a third video going over several different types of hardware expansion problems that will hopefully help you learn how to solve them much more efficiently. See ya.
I hope you liked our video, and if you did, like and subscribe right here. Do it now. I won't look. Well, maybe a little. And if you really liked us, follow us on Twitter right here.